to put this on. We really hope that you have a fantastic experience here, but we couldn't do this without the support of a number of our sponsors. So our premier sponsor this year is Boeing. We really want to give them a round of applause, and thanks for all the support helping to put this on. Our major sponsors this year are the Australian Space Agency and iSpace. And our supporting partners are the South Australian government to put this on. We really hope that you have a fantastic experience here, but we couldn't do this without the support of a number of our sponsors. So our premier sponsor this year is Boeing. We really want to give them a round of applause, and thanks for all the support helping to put this on. Our South Australian government, Defence SA, South Australian Space Industry Centre, and Drone Deploy. All right. I also want to mention that if you just go into Incarnate Wardley through the glass doors here, another partner, Mini Mammoth Games, is in there with a video game version of this challenge. They feature a couple of different rovers, and they have all of the tasks from this challenge are on the game. So we would encourage you to, when you're taking a break from working on your own real-life rover, go take a look at the ones in Incarnate Wardley and pay a visit to Mini Mammoth in there. And with that, I'll hand the mic over to Dan so we can get things going after the sponsor videos. Thank you.
Australia is a nation of creators, aviators, protectors and innovators.
3, 2, 1.
From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities. Developing new military platforms and communications networks and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia, by Australians, for the world.
Okay, are you ready? The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things, the first female Queen's Counsel, Supreme Court Judge and State Governor, all in one, first in the family with a degree, a black belt, a robot. first Aussie to walk in space. Helped detect gravitational waves. Made lots of babies. World top 100 in all. This stuff. Launched a satellite, revived lost languages, home to 1600 brainiacs, and a winery, all in the heart of Australia's most livable city. So, what's next? Make history at the University of Adelaide.
Can you hear me? Oh, hello, and we're in business. Hello and welcome everyone to the third instalment of the Australian Rover Challenge. It's truly surreal to see how many teams and how big the competition is scaling up to. So, the first competitors rolling in for the post-landing task this morning is the University of Technology, Sydney. So, this is their second year of attending the Australian Rover Challenge, and I'm really looking forward to seeing them compete. First, I'd like to acknowledge the University of Adelaide for really helping them out as they've encountered some issues in terms of the shoulder plate for their arm actually snapped at 1 a.m. yesterday. So they've been furiously trying to get their arm up and operational so that they can compete in this morning's task. So there may be some delays in terms of getting their rover out onto the pitch and onto the lander. So when we see them approaching, let's get a lot of noise and celebration for them because they've been working feverishly for the last, I'd say, 12 hours. So yes, the post-landing task, for those who aren't aware, is one of 4 tasks for the Australian Rover Challenge. And the challenge main purpose is to simulate Luna's rover mission on the lunar surface to try and emulate that of the Australian Trailblazer mission. And for those who aren't aware, the Trailblazer, which just got announced, I believe 2 days ago, has 2 Australian consortiums winning a bid to develop a fully Australian rover that will be sent to the lunar surface and land, I believe, in 2026. So some really phenomenal Australian missions that will inspire the next generation of Australian young scientists, engineers, and space enthusiasts. So, as part of the Australian Rover Challenge, the first task, the post-landing task, the Australian Space Agency post-landing task has 5 key activities. The first one is a systems check. So you will notice 4 key supply caches on the lunar surface. These have been deployed and left here prior to the lunar lander landing, and these are infrastructure that will be deployed prior to human arrival on the lunar surface, so that when humans arrive, there is a base there. There's infrastructure existing so that humans can jump straight out of the lander and start doing surface activities. So of course we have the lunar lander where the rover will deploy, descend down the ramp. We have the post-processing plant. This is where the lunar rover will deliver regolith to, process it for different materials. So you can sinter regolith, which is the extraterrestrial soil that covers the lunar surface here. You can turn that into construction materials for bricks. You can extract metals from it for in situ manufacturing. You can extract oxygen for breathing to keep humans alive for longer in space. You can do lots of different things with the materials we find on the lunar surface, and that whole supply chain is in situ resource utilization. Of course, we have the main communications tower, so keeping a key, strong communication link from your infrastructure and your rover on the lunar surface back to Earth is difficult. You need a large communications array. And of course, in the back corner, we have the solar processing plant. So, energy on the lunar surface is extremely difficult. You can't use a combustion engine because there's no air. The next best thing, sunlight. Some places on the moon can receive almost year-long sunlight, and we call these regions persistently illuminated regions. So we get sunlight to power the solar processing plant, as well as solar panels on some of the rovers. The first activity that the rovers need to do is descend down the ramp and then do a systems check. And this is to make sure that all the infrastructure is where we expect it to be and help establish the lunar base to make sure that we know where everything is and everything is operational. So the rover is going to go down the ramp, do a quick systems check of all the supply caches, and make sure it's all there. Then we have the site evaluation, which is making sure that all the equipment is operational. So you'll see some of the supply caches have status readouts, and that's to inform the rover, or the operators controlling the rover, the status of those supply caches. Finally, we have a novel task, which is the wireless communication activity. You'll notice on the processing plant, there's a small white RFID card on the bottom left, and this is to make sure that the student teams are participating in activity, a realistic activity on the lunar surface, which is wireless communication. So you can't easily plug into infrastructure and communicate with things that way, because everything is coated in lunar dust. So dust is one of the major significant issues that all the Apollo astronauts noticed after the Apollo program, is that it gets everywhere, absolutely everywhere. And surprisingly, it can be found to levitate 10 meters off the surface, because the dust is the ultra fine-grained fraction, almost the size of asbestos particles. That's why when you inhale it, you can actually get silicosis, because it's essentially jagged, crushed rock that has been pulverized over billions of years by meteorites on the lunar surface. And as you operate, as you walk around, as you do surface activities, that gets kicked up, gets electrostatically levitated, and it sticks onto everything. So NASA, ESA, all the space agencies around the world are struggling really hard to try and figure out how do you work in such a hostile environment where there will be dust on everything interacting with the lunar surface, and how do you make a barrier so that when humans go out, they don't bring it back in, because it is almost impossible to get it off surfaces. It electrostatically absorbs to the surface. So another huge issue is making sure that you don't need to plug into anything, because you can't get a USB stick and just plug it in, because you're going to get dust all over it. So wireless communication. And then the final task is, or sorry, should I say the fourth task is processing plant maintenance. So they will wirelessly communicate with that RFID tag, get some instructions of what they need to do to perform some maintenance on the processing plant. So they have some buttons, switches, a joystick, a keyboard, and they need to execute a series of instructions or interactions to make sure that they've completed that activity. And then lastly, which is a novel activity for this year, is the propellant hose connection. So you'll notice a bit of space hose coming out of the rock just in front of the processing plant. So this is to simulate the connection of pipes on the lunar surface, infrastructure. Because as we begin to extract oxygen and extract volatiles on the lunar surface, so volatiles are things like water or hydrogen, you need to transport that thing around. So there'll be infrastructure in one place, in one base, as well as infrastructure in another base. And the big question is, how do you transport those resources from one area to another? And one of them is using pipes or hoses. And the next question is, okay, on the lunar surface, we've got dust, you've got lots of hazardous environments in terms of ultra-high vacuum, extreme temperatures. How do you connect those pipes together? And it is the rover's task to connect a piece that the student teams have designed and built themselves, so giving them an opportunity to practice their engineering solutions, and then connect to a common interface that we've provided them. And that sort of leads to another point is, if you've got hundreds of different companies and hundreds of different agencies all working on the lunar surface, what is a common interface between all of them? Are they all going to be using square holes or circular holes, or like how big are their connectors going to be? The next question is, what is the standard interface that all these different organizations are going to be using? So all these problems sort of meet or have a confluence of, as we're going to the lunar surface to stay with Artemis, how do we begin to work together collaboratively and efficiently? And these are the questions that students at the Rover Challenge will have to address as they work and progress into their careers. Issues that need to be addressed over the next coming years, and hopefully the Australian Rover Challenge acts as an impetus or a basis where these questions can begin to be addressed and have some pretty novel solutions that the students come up with and demonstrate in a simulated mission on the lunar surface, which is quite phenomenal. Some other things is in terms of the actual infrastructure to progress into careers building rovers out in the industry, then they have actual experience prior to even starting that job. And then there are other complications in terms of how do you power those rovers. You can't use combustion engines. You have to use, most of the teams use LiPo batteries. And one of the difficulties with running a challenge like this is in terms of the narrative of operating in space. Most rovers wouldn't all be powered by LiPo. You would have solar panels to make sure it's sustainable over months of operation, of lunar days. And then, of course, the actual application of we are in the South Australian summer heat, and there's an atmosphere, so it's the tricky thing of designing a rover and then building it for actual terrestrial application, which is great to see some of the Australian teams coming up with novel solutions and then justifying them against, well, it's really sunny. Some of you will notice in terms of the landscape of the lunar arena, we've got a crater in the back corner. So this is to simulate the persistently shadowed regions, or PSRs, that exist at the poles of the moon. And the reason why these regions are persistently shadowed, and that just means that they remain dark permanently for up to several billions of years. So since the formation of the moon and its precession out. And the reason for that is that the construction vehicles are heavy. And to send that to the moon is going to be extremely complex, risky, and expensive operation. So some ideas are just sending rockets, using their fuel bays, the cylindrical barrels, filling it with rocks and soil, and just using those to compact the surface. So some really novel ideas. And that's the thing with space exploration. You need to think in a very circular economy. Everything you send up should have redundant applications. So if your wheels are used for driving, what if you could also use them for digging the surface? So every aspect of every piece of infrastructure should have a dual or maybe tri-purpose, that if something breaks, it can also be used. For every bit of energy that you use to traverse the surface or dig up some soil, should also have a circular economy in that you use every single grain that you pick up. So this is something that SARA are really trying to push in terms of the environmental and sustainable and ethical exploration of the lunar surface and the use of its resources. So the valley will be there to also act as an obstacle that the rover needs to traverse. And then down here in the bottom right is the large lander with the big solar panels. So these panels are simulating every lander will also have solar panels to try and get energy to the key infrastructure to keep it powered. And then we have the pile of dirt in the back left corner. And this is the RAS, the Regolith Acquisition Zone. So in the Trailblazer bid by the Australian Space Agency, you'll see in the remit is the acquisition of soil, or of regolith, sorry. So that just means digging it up with the rover and then transporting it over to the NASA payload and then depositing it in a hopper. And that will be completing the foundation services so that the NASA payload can begin its resource extraction. And we're getting the rovers, we're getting Australian and international students to do that, to demonstrate that here today, probably three or more years prior to the actual lunar surface mission. So I think it'll be an exceptional demonstration of Australian student capability prior to the launch of a fully Australian mission, which I'm very excited about. And the RAS will be there so that the rovers can practice that and deposit it into the hopper, which might be out of frame, but it's just a metal box so that the rovers can deposit the regolith in there, and then they're scored based on how much regolith that they deposit. So that's looking at efficiency in terms of mass per hour, which is a common thing used in the mining industry in terms of how efficient, how energy efficient and time efficient is your process. The processing plant is there to simulate the extraction of resources from the regolith, and hopefully as the Rover Challenge begins to progress in the following years, we'll actually get the processing plant to spit out little bricks that the rover needs to build with or make the surface more interactive. I believe we're still waiting for UTS, but I'm... 10:45? Okay. Fantastic. So the UTS team will not be competing currently. I believe the technical issues have sort of made them succumb. However, I believe RMIT are up next at 10:45. So I will leave you until then, and I hope you all enjoy the Rover Challenge. And for those watching from home, I hope you enjoy the live stream. This is the first time we've live streamed the event, and I'm very excited because I get to send the link to friends, family, and friends overseas. So I get to share the passion of what we've achieved in almost 3 years now, in such a short time, right after COVID, which was an impressive, an impressive push. So yeah, thank you, and I hope you enjoy the event.
What?
Yep.
Check.
Okay, we're back on. Yes. All right. So we're gonna go.
Hello. Can you hear me? No. Test 1 2.
Yep. Just gonna take this one.
Hello. Welcome back to the Australian Rover Challenge. Sorry for the delay. There's a bit of a delay from connecting Earth to the Moon. So, up on the lander, we have the RMIT Rover team hailing from Melbourne. They're having some issues setting up the communications, but the moment that they start moving and descend down the ramp, let's get a huge round of applause for the first team to be moving at the Australian Rover Challenge. So for those tuning in, or for those now spectating, welcome to the Australian Rover Challenge. So this is the third instalment of a student robotics competition for university students from Australia and around the world now. The goal of this challenge is to get students to design, build, and compete with lunar rovers as part of a simulated mission to the lunar surface. And the ultimate goal is to try and replicate the activities that the Australian rover, as part of the Australian Space Agency's Trailblazer mission, will complete in late 2020s. So this rover will be a Foundation Services rover tasked to do some activities in preparation for human explorers returning to the moon as part of NASA's Artemis program. And we are able to try and simulate those activities here in the centre of Adelaide, on the University of Adelaide grounds, with our simulated lunar surface, which is phenomenal. Some of the activities as part of this first task, the Australian Space Agency post-landing task, which is the rover after landing on this lovely mock-up lander that we've built, will be descending down the ramp and completing 5 key activities for points. So the first activity is the systems check. Now, each of these pieces of infrastructure are the supply caches that will be deployed to the lunar surface in advance, in preparation for the lunar rover and for humans. And the purpose of this is to make sure that before humans land, that there is existing infrastructure that is working to make sure that when they land, they don't have any issues and they have a sustainable supply chain to produce oxygen for them to breathe, water for them to drink, and food for them to eat. Now, to do this, all these supply caches have just landed on the surface. This is the lunar narrative. Landing on the lunar surface is not a simple task. You have to launch it, escape Earth's gravitational field, then traverse through space, and then descend down onto the lunar surface. And if you're on a rocket, that is not a simple or safe journey. So the first activity is for the rover to descend down the ramp and investigate or circumnavigate the lander to see if any damage has occurred, and then report this back to the base station. So the base station is where the rover is being controlled from, just behind the bleachers over here. So the students are actually controlling this rover wirelessly using their base station antenna, which you can see on the back just over here. And after that systems check, which is worth 20 points, they'll be doing a site evaluation for 40 points. And this is where the rover will go to each of the supply caches and read out the status signal, which you can see as the green text on each of the supply caches. And this is to check the status of those equipment, if there's any damage, if there's any issues, and report it back to HQ, back to base station, back to Earth. Next is the wireless communication task. So you'll notice on the piece of equipment with the little ramp and all the buttons, that is the post-processing plant. So this is a piece of infrastructure that NASA will be sending to the moon. And the goal of this infrastructure is to demonstrate in situ resource utilization. It's a mouthful, ISRU. And it's a buzzword because in situ just means in place, and resource utilization means using the resources that we find on the moon and other planets, other cometary bodies like asteroids, comets, and space, and using the materials we find there to construct, extract metals, extract water, extract oxygen for use in other manufacturing and post-processing processes. So this plant will be the rovers will have to wirelessly communicate with it using RFID, so the same technology as all your swipe cards whenever you need to swipe in somewhere. And the purpose of this activity is to try and demonstrate wireless communication or interaction of the rover with a piece of infrastructure. And the purpose of that is because you can't simply connect a USB cable or Ethernet cable from one thing to another on the lunar surface. Now, why is that? Because, as you can see, the surface is covered by sand here, but on the lunar surface, the surface of the moon is completely covered by a material called regolith, which is just a fancy word for extraterrestrial soil. And the reason why we call it regolith is because it is so different or alien or extraterrestrial because it is made by the pulverization of the lunar surface of rocks by meteorites for billions of years to the point it becomes an ultra-fine sand. The particles become so fine it becomes a dust that are smaller than smoke particles that we can actually breathe in, and you can actually get silicosis from it. So you have silicate grains, which are the tiny crushed rock, and the same way that you get asbestosis by breathing in asbestos, you can get silicosis. And this is the reason why dust, lunar dust, the fine-grained rock particles on the surface of the moon, is one of the greatest risks to humans and rovers and robotics returning to the lunar surface. That was identified by Soviet and American missions to the surface, and particularly the Apollo astronauts. So if you go through the mission files or listen to some of the audio of the Apollo astronauts, it is almost entirely them just complaining how dusty the lunar surface is. It gets everywhere. It sticks on their clothes. It gets in the seals between their spacesuit. So it poses a real risk. Imagine you're an astronaut going out on the lunar surface and you can't close the gasket on your glove because it's covered by dust. So wireless communication is essential. The next task is the post-processing plant maintenance. So with that wireless communication, the teams will download some instructions encoded on the post-processing plant to tell the rover what they need to do to perform maintenance. And maintenance in this scenario is pressing some buttons, typing on a keyboard, potentially moving a joystick and flicking a switch. And the reason for this is we want to try and test the student teams how good their robotic arm is. So you'll see on the rover up on the lander here, a fancy large robotic arm with linear actuators and carbon fiber tube, which looks very impressive. This robotic arm is used to interact with the environment. So sending a rover to the moon is great, but if it can't do anything on the surface, it needs to have some sort of mechanism to interact, to be able to pick up things, to press buttons, to do actual maintenance. So this task gives the students an opportunity to use their robotic arm that they've spent sometimes years developing to actually interact with the surface. And you may think pressing buttons, typing on a keyboard and moving a joystick is relatively easy, but it is not easy when that robotic arm is attached to a rover that is remotely controlled and fed through camera streams back to a base station with some delay. So it is a face value simple, but in practice, very, very difficult task. And I cannot wait to see the teams attempt it to see how they go. And the last task, which is the most novel one, I think, which is new for this year, is the propellant hose connection. So you'll see connected to the space rock out in the center of the field is a space hose. And this hose is meant to give the teams an opportunity to practice connecting and building infrastructure on the lunar surface. So as with all things, with any resource, you need to transport it around. So we have infrastructure on Earth that transports around gas, sewage, water, fuel, all sorts of things. And we'll need that same infrastructure if we want to go and survive on the lunar surface. So NASA have actually just announced a several $million grant to develop piping or infrastructure on the lunar surface, and you need to actually connect those pipes together, and that's exactly what the rovers will do. But we've expanded on that, and we've asked the teams to design their own connector. So a big question that has yet to be addressed is, as you're building infrastructure on the moon, what is the standard interface? Like we have, a USB connector, which is standard for computers, but as you have hundreds of companies, several space agencies around the world, and they're all designing independent systems, how do they interact? Do they all use a square plug or a circular plug? Do they use plugs at all? What's the standard communication or interfacing network? And we've asked the teams to design their own one and interface with a standard connector we've designed. And I think this is fantastic because it's giving the teams an engineering challenge, a practical engineering challenge that they need to solve through designing, building, prototyping, testing on the rover and demonstrating it here at the task today. So each of these activities will be broken up into discriminate points, and you'll be able to track the points up on the fantastic Jumbotron screen we have at the back of the arena. And I'll also be updating you when a rover completes an activity so that you can stay up to date on cheering on the competitors and making sure that the teams get the loud noise that they deserve after designing, building, and staying up many, many late nights and getting much less sleep than they deserve to build these rovers, fly them over here to Adelaide, and compete as part of a lunar surface mission. So while we wait for RMIT to get moving, I will leave you with some fantastic music and as well as some slides to show the current leaderboard score points for all the teams, which they've submitted some critical design reviews. So as part of any spaceflight mission, you need to submit reviews iterating the progress of that payload or that flight system. And one of them is the critical design review and the system acceptance review. And these are submissions that the teams have all sent to us. We've marked, we've given them feedback from industry leaders, and they've gotten points. So there is a leaderboard with points. And with that, I will leave you with some music. So if you're tuning in, right now we're witnessing in situ maintenance. So we've got some astronauts servicing the rover, and right now they're trying to establish some comms from their base station antenna down to the rover, so that the base station operators, which are out in a remote HQ base back on Earth, can communicate with the rover and get it moving. So they've got, I believe, 17 minutes left of the task time. So we'll see if they can try and get some points for this task and really secure themselves a solid position. But one thing people should remember is that building rovers and testing them is no simple task, especially when you need to fly a rover interstate or overseas and get it all working as it was in your workshop or wherever you were testing. So once they get moving, let's get a huge round of applause, and yeah, let's see some rovers moving at this third installment of the Rover Challenge. So we've got 3 minutes on the clock until the RMIT, 2 minutes on the clock, until the RMIT post-landing task is over. So we'll see if they can get moving and get some initial points. But otherwise, we have up next, coming from all the way in Wrocław, I think I've butchered the name, in Poland, Project Scorpio. So this is Australian Rover Challenge's first international competitor. And this is a huge milestone for both the Australian Rover Challenge, but also the connection for students getting to see how rovers are designed overseas and getting a novel insight into the many different approaches of how you can design, build, and execute with a rover. So as the clock ticks down, I'll just remind everyone, if any new spectators or people watching from the live stream, welcome to the Australian Rover Challenge. We are a university student robotics competition, providing a platform or a simulated lunar mission or a surface to let university student teams design, build, and compete with their rovers. And the purpose is to try and simulate the very activities that these students may be working on as part of the Australian Space Agency's Trailblazer mission, which is sending a lunar rover to the moon in later in the 2020s, potentially even as early as 2026. So this task, this Australian Space Agency post-landing task, has 5 key activities where the teams can score points. The first activity is the systems check, worth 20 points, where the rover needs to descend down the ramp and perform a systems check of the lander to see structure as it is landed on the surface. Next will be a site evaluation worth 40 points. And you'll see out on the surface some key pieces of infrastructure or supply caches, including a post-processing plant in the back corner, a communications tower in the center, and a solar processing plant with solar panels on the small hill in the other back corner. And the rover's job is to go investigate each of these supply caches to see what the status readout is, to see if those pieces of infrastructure also sustain damage and what activities the rover needs to do. The next activity is the wireless communication. And it looks like RMIT is unloading their rover, and they're done. So first off, let's get a huge round of applause for RMIT. I'm sure we'll see great things from them as they compete in tomorrow's task, the excavation and construction task. And I'll remind everyone that operating a rover under competition conditions is very stressful and very difficult, as they've traveled all the way from Melbourne and packing up a rover, sending it interstate, and then redeploying it out here on grass is no easy feat. So coming up now is Project Scorpio, all the way from Poland, with their rover, Scorpio. And their task start time is 11:30. Yeah, huge round of applause for... So they are slated to start at 11:30, so in 4 minutes. So, as I was saying, activity number 3 is the wireless communications task. And you'll see over at the post-processing plant, in the bottom corner, a white RFID card, which is the same card that you'll use for swipe key access to any offices or buildings that are around common workplaces. It is the rover's job to drive up to this RFID card, wirelessly communicate with it, download instructions, and then perform maintenance on the post-processing plant. And that maintenance allows the teams to use their robotic arm, which you'll see mounted to the top of the rover. And these robotic arms enable the rover to interact with the environment. So a rover needs to perform several foundation service activities, including moving obstacles, performing maintenance, interacting with the environment generally. And for this task, the rover will download some instructions, which will include interacting with buttons, switches, a keyboard, a joystick, in a sequence. And if they do those tasks correctly, they'll receive points for each little activity that they do. And finally, a novel inclusion for the task at this year's installment of the Rover Challenge is the propellant hose connection. Now, you'll see coming out of this very real fake space rock out in the center of the pitch, a space hose. And this hose is meant to simulate the development of infrastructure or pipeline infrastructure to transport resources around, like rocket propellant, rocket fuel. And that's what the processing plant is meant to try and simulate, is the extraction of resources, critical metals, volatiles from lunar regolith, the processing of that into usable products, including rocket propellant or oxygen for life support systems or sintered bricks for construction. And it is the rover's job to connect the hose to the processing plant to establish this lunar surface base so that when the humans arrive in a couple of years, the infrastructure and the resources are there ready to go so that they can begin their surface activities. So one interesting aspect of this challenge, the propellant hose connector, is the end piece, the connector as on the other end of the hose, was designed and built by the students. And we've designed and built the other end of the connector on the processing plant. And this is an engineering challenge where the students need to design their own innovative solution of how to connect to the hose. So we gave them the schematics, but the purpose of this activity is to address a really fundamental question, which isn't too obvious, but raises the question of, as companies and space agencies and humanity returns to the moon and stays, how do we all interface? How do we communicate with each other? Every different design of a piece of infrastructure may have a different connector. So it raises a question of, what is the standardized interface design and communications protocols between different missions from different countries and different organizations. So this is a small taste of what they may have to do once they're working in the space industry, is designing a standard interface connector for their rover to connect with another piece of infrastructure. And with that, it is 11:30, and the start time for Project Scorpio has just begun. So the moment we see their rover start moving and descending down the ramp, let's get a huge round of applause for our first international competitor. Now, the astute of you will recognize that the rovers are being controlled remotely. So there's no cable connecting the rover to the base station or the operators in the base stations at the back of the bleachers. So this is simulating what would likely happen as we send rovers to the moon, is that you'll have operators on the Earth communicating through radar to a rover or infrastructure on the lunar surface. So for these rovers, for these teams here today, we're operating on public frequencies, so 2.4 or 5 gigahertz commonly. But on the moon, there are several things like GPS or 5G or some standard communication protocols that don't exist because there's no infrastructure, because it's the moon. And that raises another interesting question of, how do you... And there we go. They're moving. So a huge congratulations for Project Scorpio moving, descending down the ramp. And with that, they've scored the first 5 points for this task, which is descending down the ramp. And now their next activity is to perform a systems check. And this is where the rover is expected to circumnavigate the lander and note any damage that has happened. And you will note at the back of the lander there will be some information about that. So it is the rover's task to convey this information back to the base station operators, and the operators are getting all their information purely from the rover. So they are completely air-gapped, so there's no information traveling from the surface to them except through the rover, and this comes through cameras positioned on the rover, so you'll have a live stream as well as pictures and other sensors that the rovers have included in them. And after this task of this systems check, the rover will then have to go perform a site evaluation of the other pieces of infrastructure. So this is simulating what a rover would actually have to do on the lunar surface. Is as you've ballistically descended your infrastructure, so you've landed it on the surface using a retro thruster, that can cause a lot of damage. There's a lot of vibration, a lot of forces acting on your infrastructure. So it is the rover's job to see, is everything safe? Is everything operational? Is everything still working? And that is what the rovers are currently doing. Yeah. So with that, I can confirm that they have completed activity 1 for 20 points. They have imaged the status readout on the back. So another huge round of applause as they're crunching through the task. They still have, I believe, 40 minutes to complete the other 4 tasks. So now there are 40 points up for grabs for activity 2, the site evaluation, where the rover now needs to traverse to each piece of infrastructure and again read out those status readouts to see what is the status of that infrastructure. So one thing that is prevalent on the lunar surface is the amount of solar illumination, so the amount of sunlight that reaches the surface, as well as the angle of that sun. So visibility is a huge issue as you're deploying rovers to the lunar surface, as sometimes it can be so bright or so much glare, like today's gorgeous summer day in Adelaide, is that sometimes reading things or taking observations is quite difficult, so there's lots of glare. And the interesting thing is, as you go towards the poles, so the north and south pole of the moon, because the moon rotates almost perpendicularly on its axis, and that just means, imagine if you've got a basketball spinning on the top of your finger, it's spinning on a single axis, and that's what the moon does. So because the sun is hitting it almost directly on the side, as you go towards the poles, the sun gets lower and lower on the horizon, so you have some really steep sunlight grazing across the surface, making visibility extremely difficult if you're viewing things through the lens of a rover. So you can have really long, drawn-out shadows. You can have really bright patches right next to really almost entirely dark patches. And this is a technological issue that needs to be overcome as we visit the poles for the first time. So out of all the Apollo missions and the Soviet missions to the lunar surface, out of all the missions throughout the late 60s and early 70s, they only visited the equatorial regions. So all our understanding is from a thin band across the equator of the moon. So we've never directly explored the poles. So there are many outstanding questions that we just don't know the answers to. Like, what is the material like there? Is the ice, does it exist at the poles? Is it like sheets? Is it granular ice? What is the morphology of that? And that raises some really interesting questions of, as we want to access water on the moon to use for, growing agriculture, growing food for our astronauts, splitting it into oxygen to breathe, using it for rocket propellant, rocket fuel. If we want to access that water, how do we dig it? How do we actually get at it? So the rover now is traversing through the very hilly, extreme terrain area, and I believe they've achieved 20 points after imaging the status readout on the communications tower, as well as the solar panel. So you'll notice that it is trying to traverse past some large rocks, and rocks on the lunar surface can come in a range of size from sub-micron all the way up to huge boulders that, in the distance, because there's no atmosphere, can really play with the human psyche. So the Apollo astronauts sometimes saw small boulders which they perceived as huge hills, and sometimes huge hills were perceived as small boulders. So gauging distance on the lunar surface is extremely tricky, and something the Apollo astronauts actually had to be trained on. And it's also difficult for a rover. So if your rover is trying to traverse some difficult obstacles, it needs to figure out how far away is that obstacle, how big is it, and is it a hazard? And this is important because as rovers drive on the surface of the moon, you can't drive them like an RC car like we are doing today. There is a delay. It's about 4 minutes. So the rover needs to be able to drive around autonomously or semi-autonomously if you give it a set of instructions. And this is one of the tasks that we'll be doing on Sunday. So the Boeing mapping and autonomous task, where the rover has to, like today, traverse the site, identify where different obstacles and key points are, and then as it's doing that semi-autonomously, mapping the area, so finding the distance between things and generating a map so that when humans visit that area or when people are operating the infrastructure back on Earth, they know where everything is because there's no GPS, there's no reference point on the moon. So it's really tricky to figure out simple questions like, where am I? And where is that rock? Or where is my lander? Because there's no reference point. So in the coming years, I think later this year actually, there will be several private companies sending rovers to the moon to try and address these questions. So now the team is attempting the wireless communications task. So you'll see on the bottom of that processing plant, a small white RFID card. And this is the same thing as the common swipe cards that you use to access your building. And the purpose of this is to try and get the teams to practice wireless communication, so downloading instructions from the processing plant wirelessly. And the reason why we're getting to do them wirelessly is because the lunar dust, the dust that covers the lunar surface makes connections like USB-C or Ethernet, like a plug, very difficult because you'll just get dust coating the connections. So here they go attempting to communicate wirelessly. They probably have a RFID receiver on the end of their arm, and they're going to attach that, tap it with the RFID card, sort of like how you get access to a building, and they're going to be downloading instructions to perform maintenance on the processing plant, which is that piece of infrastructure there. And those instructions will include a series of instructions of what they need to do with their robotic arm. So a series of, if they need to press buttons, type on a keyboard, flick some specific switches, to get the processing plant up and running so that the base, this lunar base, can start becoming functional. So the rover, this task is trying to get the rover to figure out where everything is, make sure it's all working, and then get the base up and running, getting it functional so that when humans arrive, the infrastructure's there, the water's on, the lights are on, and everything's working. So right now the rover's trying to get that communication, that connection between it and the RFID tag to download those instructions to figure out what it needs to do for the processing plant maintenance. So if any of you have ever tried to plug in a USB and you go one way and then it doesn't work, and you go another way and it doesn't work, and you go another way, it doesn't work. Sometimes that happens with RFID. You've got to get a really nice, flat, even connection. And with a rover, with wheels, with a robotic arm that you're controlling remotely, sometimes that isn't always perfectly lined up. So this is a fantastic challenge for them to try and get that alignment and get that communication and get all these moving parts working as they need to complete this activity. And this is the third activity out of 5 activities. So this one is worth 10 points just to make that connection. They'll download instructions and then begin activity number 4, which is the maintenance, worth 20 points. So they'll have to do 4 different things, and each interaction is worth 5 points. So if you can, for those watching the live stream and those who can see the screen as well, you can see the very fine movements the team is trying to do with their robotic arm. And it's quite tricky because you're interacting with a surface that you can move the robotic arm in several different degrees of freedom, as well as based on the position of your rover. So this relatively face value simple task involves a lot of pre-thought and precognition of how does our system work, how do we operate it, and how do we actually execute this task. So the operation of a robotic arm is quite difficult as well, based on the engineering of how much backlash do you have. So you'll see that every now and then those fine movements, sometimes it'll move and then it'll wobble a little bit. So that's some of the slack in the system. So with removing backlash and removing slack and really over-engineering your system, sometimes you can get really precise movements. So, and that's the difficulty with how accurate is your system. How can you make it accurate and precise and strong to lift heavy weights, but also how do you make it lightweight? How do you make it cheap? And these are really fundamental questions of faster, lighter, stronger that all engineers must address. And these students are getting to practice that with a fully simulated mission, which is demonstrating really high technological capability and really tying in what they're learning at university and making it practical. So these are the skills that they will need to demonstrate as they go into the workforce. And we hope that the Australian Rover Challenge acts as a platform for them to really get the experience and capability, and for them to succeed and strive in the Australian and international space industry. So you'll see now the rover has downloaded the instructions and it is attempting to perform a series of very complex interactions, including potentially typing on a keyboard, pressing buttons, moving a joystick, flipping a switch, and performing some very high fidelity movements, the use of the robotic arm. So then again, this is trying to get the students to practice, put in practice all the design and development and testing of their robotic arm to perform some very fine motor skill movements. And it looks like they'll be attempting to type on a keyboard. Now, for each successful movement or interaction, they will receive 5 points out of an available 20 points for this task. And once they are complete, they will move on to the next task, the final task already, with I think 30 minutes on the clock for the propellant hose connection. So that is the hose connector, or the hose, the space hose, connected to the rock just on the surface. And this is trying to get the teams to have a really unique opportunity of designing their own interface connector to develop some infrastructure on the surface. So making a connection from the processing plant, which is extracting volatiles like water or oxygen and hydrogen from the lunar soil, the extraterrestrial soil that we call regolith, and then trying to get that hose connector to a lander so the rockets can come in, refuel, and then go back out into lunar orbit. So the goal, or the long-term horizon goal of this base that you see, is to act as a resupply depot for infrastructure and rockets and rovers on the lunar surface to make a cislunar economy, a cislunar industry. So much like today, how we have rockets launching, servicing satellites with the International Space Station, in the not so distant future, we'll have a orbiting gateway, so the gateway designed by NASA, orbiting the lunar surface, or orbiting the moon, with humans staying there and ferrying resupply missions and doing research activities in orbit and on the lunar surface. With that, it looks like they've completed activity 4, the post-processing plant maintenance. Look at another round of applause. And now, with many minutes left on the clock, they're attempting arguably the most difficult task, I think, is the propellant hose connection. So the rover is now going to pick up the space hose that we've made, and the Project Scorpio team have designed and built or 3D printed their own connector on the end of that hose. And it is the rover's job to now grab that connector and plug it into the cognate receptor, or the other end of that hose connector, which we've made on the processing plant. So that is a standardized connector that we've made, and it is the rover team's job to design their own connector, which will interface with that and plug in to make a pipeline that will resupply rockets or rovers on the moon. So as we get the close-up view of the end effector on the robotic arm trying to position itself to grab the connector, you'll see that most of the robotic arms have several degrees of freedom. And what that means is for every axis that the robotic arm moves, so it can rotate at its base, it has a shoulder joint, it has an elbow joint and a wrist joint, each of those movements provide a degree of freedom. So some arms have up to 6 degrees of freedom, which is very impressive for a student team to design and build. And it is even more impressive to get that movement into functional and knowledge of where the robotic arm is in space to reach out a very long distance and interact with objects. So their end effector looks like a claw mechanism, and that raises a good question of, if you're designing a robotic arm for space, what does that arm look like? What does the hand look like? Is it 3 fingers? Is it 2 that clamp down? Should it be any other design that you can think of? And the exciting thing is that there's no right answer and there's no wrong answer. So one of the exciting aspects of the challenge is that we get to see how different students from around the world approach this task, and see how they design the robotic arms and hands and how they in practice as part of a simulated mission, how it performs. For those new spectators joining us and for those watching the live stream, you are witnessing Project Scorpio with almost 20 minutes left on the clock, completing the last activity of the Australian Space Agency post-landing task. And this task is trying to simulate the lunar rover descending down the ramp and checking on all the infrastructure that has just landed on the lunar surface to make sure it's all operational and functional, and then perform some site maintenance. So interacting with the post-processing plant, so the switches and buttons, and then connecting a hose to try and set up some infrastructure to resupply rockets and rovers coming into land as part of a resupply base on the lunar surface. So this final activity, which is worth 10 points. So you'll notice that each activity in the task gets harder and harder, and there's less and less points, and this is to try and make it so that each task is more and more difficult the further you get in. And this hose connector was designed and built by the team, and then it's their job to connect it to the other end of the connector that we've made on the processing plant. And this movement is, at face value, rather simple, but in practice extremely difficult, because the rover is being operated remotely by the students back in a base station, which is the tent, and that's meant to simulate the operators back on Earth operating the rover, and the only information or input they're getting is the cameras on the rover. And I can tell you from first-hand experience, the view that you get on a rover with cameras isn't the best. So it's very difficult. And it's a fantastic challenge of figuring out where do you put cameras on the rover, what view is best, because you can't get cameras everywhere because it's a lot of bandwidth and a lot of data you need to stream down, as well as what type of cameras do you use. Do you use a simple camera? Do you use a camera that pivots on a 360, like the security camera they've got mounted to the top of their rover? Do you use a fisheye lens? Do you use one with zoom? Do you use an actual camera lens from a high fidelity camera? And these are questions that need to be addressed as well. And it looks like they've managed to pick up the hose clamp or the hose connector, which is fantastic. And now it is their job to try and connect that to the connector, and we'll see how they go. Because first they need to position the rover, then they need to position the arm, then they need to try and get the alignment and actually push it into place. So lots of moving parts, lots of theory and design and development, probably over the last year to get to this point. And let's see how they perform with 20 minutes on the clock. I haven't had the opportunity to see exactly the design of the connector that the teams have used, but most teams have designed and 3D printed their connector. And for those who aren't aware, 3D printing is the technique where you melt down plastic and you deposit it layer by layer, and you can develop or rapidly prototype any object or shape within parameters. And this has enabled teams to speed up the rate of development and testing and prototyping by orders of magnitude compared to relying on machining and manufacturing, which the teams can also do themselves. But 3D printing has really accelerated the development and enabled the success of student engineering challenges like the Rover Challenge, because not every piece that you need for a rover is available from Bunnings. So a lot of the things that they design and build are done by 3D printing, and it's lots of fun. And for those with children interested, 3D printing is relatively accessible, so you can buy a 3D printer from some stores online. And it is a fantastic opportunity to learn about the design process and material science, and you can print fun toys. So you don't need to go to the store anymore, you can just 3D print your own toys. So very exciting. And you can use it for applications for the lunar surface, for space exploration. With 10 minutes left on the clock, this simple task shows just how difficult it is to try and connect two connections from a hose to a processing plant. So this is really challenging the students in terms of getting the positioning of the rover, the operation of the robotic arm, the movement of the robotic arm, and the alignment of the connector that they designed and built in-house to do this last task, which is the connection, the final connections of infrastructure to deploy or to set up a base on the moon. So we'll see how they go with 10 minutes left on the clock, and if they can get these last 10 points remaining for the Australian Space Agency post-landing task. And for those tuning in on the live stream or the spectators watching up on the Jumbotron screen, you can see the complexity of a robotic arm with several degrees of freedom. For every movement you use in one plane, the rest of the robotic arm or that hand, that wrist joint also moves. So The alignment of the connector to the hose is quite a complex sequence of movements and alignments and corrections that the team needs to do in real time. Just a quick shout out, the joystick you'll see just to the above right of where the wrist effect is actually a joystick used for a 40-year-old Atari console. So a little bit of history. So we started with 20 minutes on this single activity, and now we're down to 5 minutes left on the clock. Let's see if Scorpio can execute and perform with this final activity. This is just showcasing the complexity and difficulty of using a robotic arm or a manipulator on the lunar surface to perform high fidelity activities. So as we return to the moon with the Artemis program, which is going to put a woman on the moon in this, which will herald a new age of us returning to the moon and staying, we will need to set up infrastructure. We need to keep humans alive, and we need to keep them safe, and we need to do so in a sustainable manner. So we can't ship everything to the lunar surface. You can't take all your water, sandwiches, and fuel with you. You need to use the resources that you have available on the surface. And one thing that is abundant on the lunar surface is dirt, specifically extraterrestrial soil that we call regolith. So you can actually heat up this, it's essentially crushed rock, to extract metals. You can extract volatiles like hydrogen and oxygen. You can recondense those to make rocket propellant, or you can make oxygen for humans to breathe, and you can use that as well to grow food, so agricultural ecosystems. And it all starts with a single connection to make sure that when you extract those resources, they go somewhere, they're transported by pipes. With 2 minutes left on the clock, it looks like they're doing a readjustment of the robotic arm to try a different attack angle. Let's see if this bold maneuver will play off with 2 minutes. I believe the robotic arm is using a secondary system on its elbow joint to try and twist the knob, perhaps. I think they're trying to attempt one of the last activities for the equipment maintenance, the processing plant maintenance. With less than a minute left on the clock, let's see if it pays out. So it looked like the robotic arm was actually reversing up, positioning its elbow joint with a rear end camera so that it could reposition and pivot to try and... Yeah. And with that, it is the end of Project Scorpio's run. Let's get a huge round of applause for an almost flawless run, and a huge shout out for them traveling all the way from Poland with their rover in suitcases, at a very red-eye, I believe 5 a.m. flight. So a huge shout out for them and a fantastic effort for their first participation in the first task of the 2023 Australian Rover Challenge. Thanks, John. Up next, we have the Monash Nova Rover team hailing from Melbourne in Victoria. You will notice their rover is a fantastic and lovely hot pink, and this is an initiative to raise awareness of female and young women engagement in STEM to showcase what you can achieve in robotics, and it is a fantastic initiative that I'm fully supportive of, and it just looks absolutely cool. So I wonder if we can get a hot pink rover to the lunar surface, because it'll stand out. It'll definitely stand out against the white backdrop of the lunar surface. So the start time for Monash for the post-landing task is 12:15. So they have a few minutes to set up, establish communications with their rover and the base station, and then they're all performing the same tasks as Project Scorpio, which will be a sequence of the systems check, where the rover needs to drive down the lander, inspect the lander for damage, report back to base station, perform a site evaluation of the other pieces of infrastructure on the surface, see if they're still operational, if any status readouts are not what they expect. Then travel to the post-processing plant, download some maintenance instructions using RFID, which is the same technology as your swipe key card to access buildings, and then perform maintenance on the post-processing plant. So that may include switching switches, pressing buttons, moving a joystick, typing on a keyboard, and and to make sure that that processing plant is up and running and operational. And then the last activity is the hose connector. So that space hose has a hot pink 3D printed connector that the team has designed themselves. All teams have designed a connector that they've designed, tested, printed themselves, and their job, their task, although it seems simple, has been demonstrated to be highly complex, is to connect to the post-processing plant, and that last activity is worth 10 points. So with a few minutes left on the clock, I'll let the team set up, and once they start, I'll let you know. With that, it is 12:15 at the start time. The start time is on the clock for Nova Rover. So they have 5 activities to perform, which will include, up on the screen, you can see the systems check, the site evaluation, the wireless comms, plant maintenance, and propellant hose connector, worth a total of 100 points. The rover is tasked with establishing or figuring out the surface, if the infrastructure is all operational, if it's safe, if it's functional, and then performing a series of tasks involving the robotic arm, which will be used to perform site maintenance, so switching buttons, as well as making a connection with their hose. So all this input, all the remote control of their rover is being fed live to a crew of operators down in the base station, which is a fancy tent out the back of the bleachers. And all that input being received by the team is via live stream video cameras placed in various areas on the rover. So let's see how they perform. And yeah, it's a beautiful summer day here. Luckily, no rain. I believe we had rain 2 days ago, and that is a huge issue that, of course, wouldn't happen on the lunar surface because there's no atmosphere, there's no water, liquid water at least. Now they're verifying that the control of the rover is all functional. So you can see the rover wheels moving forwards, backwards, pivoting on point. So the functionality, or I guess the advantage of having pivot steering for each independent wheel, allows you to turn on the spot as well as strafe in 2 axes, so left, right. The advantage is that compared to normal steering like have on a car with 4 wheels static on an axle, is that to approach different points of interest, you would have to drive forward and then turn. If any of you have ever reversed with a trailer, you'll know the plight of not having pivot steering for each independent wheel, whereas rovers in this way are able to approach interfaces like the processing plant at a non-advantageous angle, then readjust perfectly so that the robotic arm has less movements that it needs to perform. This requires a lot of control, testing, so my hat's off to Monash Nova Rover for coming to the challenge with this control system functional. Up on the screen right now, you can see the current leaderboard. You'll notice Project Scorpio number 1 with a score of 135. That is because they are the first, and we're moving. Let's get a huge round of applause. So this is the Waratah Rover, I believe, from Monash Nova Rover from Melbourne. Currently descending down the ramp in a very controlled popcorn sounding manner. And that is the sound of the 3D printed grousers on those hot pink wheels interacting with the metal grate of the lander. And you can see the pivot steering coming into play there with a very smooth arc as it begins to strafe. Very impressive. So the first activity that the Waratah Rover will be completing now is the systems check, where it needs to circumnavigate the rover and evaluate if there's any damage to the lander as it descended down with its retro rocket thruster when all these pieces of infrastructure were deployed. And it looks like they just rectified one of their wheels, which was pivoted off to the side. And this is just highlighting in a very visual manner some of the amazing design work and control system manufacturing, integration and testing done by undergraduate students. And luckily, the platform of what the Australian Rover Challenge aims to do is give students the opportunity to showcase what they're learning at university and put it into practice in an environment that is enables them to do things that they can't do anywhere else. So this gives them extremely sought after skills and expertise of designing, integrating, working in a team environment, so the soft skills of management, leadership, as well as the practical skills of actually building a rover and a high quality rover that can perform a series of tasks. So it is now coming around to the rear of the lander to try and read out the status readout to see what's wrong with the lander. That information will be relayed back to the base station team, so the team back on Earth. And then with that, they will be attempting 4 other activities out of 5 for a total of 100 available points. So now you can see up on the jumbo screen and in person that individual pivot steering for each wheel coming into play, where the rover can pivot on a dime, allowing it to really take advantage of that highly dexterous movement or maneuverability that you can't really achieve with normal skid steering that you would have on a car. And confirmed they've completed activity 1 and received 20 points for the first activity, so a huge round of applause. And with 30 minutes left on the clock, they are now going to go attempt activity 2, site evaluation. And it is the rover's job now to visit each of the sites, the infrastructure out on the field. So we've got the communications tower relaying the information back to Earth. We've got the solar array panels providing power to the different pieces of infrastructure on the surface, as well as the post-processing plant down in the back corner, which is where the regolith, this extraterrestrial soil across the surface, will be processed to yield useful resources, which can include metal for making steel and making wires on the surface for reusability, building infrastructure, repairing infrastructure. You can extract volatiles like oxygen and hydrogen, which you can use for rocket fuel. You can combine that for water to make to start growing food on the surface of the moon, and you can also use it for other post-processing techniques. So in the not so distant future, there could be a huge industry on the lunar surface taking advantage of in situ resource utilization, which is a buzzword commonly used, ISRU. It's essentially using what we find out there in space to do the things that we need to do commonly here on Earth, which is manufacturing, processing, making things. And the advantage of that is it means that we don't need to ship, we don't need to launch everything with us. We don't need to take all our water and sandwiches and fuel and metal. We don't need to launch it off the ground, which is extremely expensive because every kilo costs money. It is also dangerous because high mass rockets are tricky and complex, as well as it is also efficient in terms of if you need a part, if you need something on the lunar surface or on Mars or on a comet or asteroid, you don't need to wait for a resupply mission. So you can just survive out there sustainably, economically, and ethically as well. As we're waiting for the rover to potentially re-establish connection or try and get that back wheel dislodged, I'd just like to acknowledge the sponsors enabling this rover challenge to exist. So your contribution and your support is directly enabling the growth of the next generation of space enthusiasts, which can include anyone from science, engineering, humanities, business, arts, for visual representation of everything that the students do. As we go into space, one of the key things is that we need everyone. It's not just engineers and scientists going to space, it's humanity. So if you have a passion for working together in teams and contributing to the next step in human growth, we need you. So his exciting thing is if you have any children or if you're interested in space, get out there and just get some, find what you're passionate about and apply it towards a space application. And there's more connections than you may realize. As the Monash Nova rover team continue to troubleshoot, I just want to highlight that driving rovers on the surface of Earth isn't tricky, and that's just going to highlight how difficult it is going to be driving rovers on the lunar surface. So one of the main applications of this Australian Rover Challenge is to try and get students involved and engaged with the recently announced, or recently winners announced, for the Australian Space Agency's Trailblazer program, which is an Australian mission to the moon. So we are going, and we're sending an Australian-built rover, a Foundation Services rover, to perform some activities on the lunar surface as part of NASA's Moon to Mars initiative. So we're partnering with NASA to get Australian involvement to put an Australian-built thing on the moon, which is, the goal is to sort of demonstrate that we Australians can do this and to inspire the next generation, because you can't be what you can't see. So as soon as we have an Australian payload on the surface, I cannot wait to see the next wave of space enthusiasts rolling through school, rolling through university, and eventually joining us as we progress into the space industry. With 25 minutes left on the clock, I just want to recount some history. So when we started the Australian Rover Challenge back in 2021, right after COVID, which was quite an interesting way to organise a challenge, we started with 3 teams, 3 Australian Rover teams. The Monash Nova Rover team, the University of Adelaide and RMIT. Since then, we've now grown to in excess of 8 Australian rover teams. And this is just highlighting the exponential growth of students engaging in robotics, building rovers, as well as the presence of Project Scorpio from Poland, highlighting that we're now growing to an international stage. So there are other rover challenges around the world. Oh, and they're moving. Let's go. Let's get a round of applause. With 25 minutes left on the clock, they have 4 more activities to do. So they're currently attempting activity number 2, which is site evaluation, worth 40 points. So it is the rover's job to traverse to each of the pieces of infrastructure, read out the status readout on that, for example, the communications tower, and relay that information back to the base station so that the ground crew can figure out if everything's working, where everything is, and to make sure that this is the first sort of activity that a lunar rover would have to do on the surface, which is evaluating the site and making sure that everything is where we expect it to be and everything is operating as we expect it to. One of my favorite things about the Rover Challenge is that because every student team is acting independently, you get to see some of the range of different approaches to design, engineering, and practice of building a lunar rover, because there's no schematic. When you're in your undergrad, no one tells you how to build a rover, so they're all doing it themselves. So my favorite thing is to see just how different all the rovers are. Some rovers have 3D printed wheels, like the rover you see in front of you, with the steep grousers. So those are the fins on the edge of the wheels that allow the rover wheels to have traction in this loose material, as well as Project Scorpio, the team prior, which had a fabric covering the wheels, providing a different type of traction. And it's exciting because when you're designing for extraterrestrial vehicles, there's no right or wrong answer. There's just different approaches that work differently for different applications. So it's an exciting engineering challenge because it enables the students to really have a lot of design freedom and to practice innovative solutions that allow them to really have that freedom to design and build in a novel way. So it's lots of fun, and it provides a platform that you can't really get anywhere else. little maneuver is the strafe, demonstrating the advantage of having that individual pivot steering for each wheel, and it allows the rover to strafe around sort of like a crab in two different directions, and also have these really nice smooth arc turns. It looks like it has received the readout for the the solar array panel, and is making its way through the extreme terrain of hills and rocks. Now it is progressing to the last piece of infrastructure, I believe, the post-processing plant, and with that it will be completing activity number 2, the site evaluation. And with that, it looks like they've completed activity number 2, site evaluation. So now they are attempting activity number 3, the wireless comms, which is interacting with that little white card, the RFID card, which you commonly use for swipe key access to buildings at your workplace. And this is trying to showcase the wireless communication required to download and relay or upload instructions on the lunar surface, because you can't use things like USB-C or Ethernet cables, because there's a layer of dust that coats essentially everything. And this dust is essentially extremely fine-grained, smaller than particles of smoke. So, and it's all crushed, jagged rock. And as that sticks to things, it scratches, wears down, abrades everything, including the gaskets that connect astronaut outfits. So it raises a lot of issues in terms of after the Apollo astronauts returned home, their faceplate visors were almost entirely scratched. They couldn't look through them anymore. Or their gaskets wouldn't connect as efficiently, which raises issues of if you have a leak in your spacesuit on the lunar surface, how do you fix that if you can't get the dust out? And as well as if you're trying to download information, you can't use USB-C. You've got to wirelessly communicate, so you don't have to worry about that dust issue. So the rover will be downloading information, some instructions to perform maintenance on the processing plant. And those instructions will include a set of activities, including pressing buttons, moving switches, typing on a keyboard, moving a joystick. And once they do those successfully, they'll be awarded up to 10 points. Sorry, 10 points for the communication and then 20 points for performing the maintenance. And with 13 minutes left on the clock, so their end time is 12:55, let's see if they get through the last remaining 3 activities in time. So it looks like the rover's trying to get the perfect alignment of the RFID card. And they've downloaded the instructions, they've received the instructions for performing maintenance, and now they will be attempting to interact with the panel. So switch some switches, press buttons, type on a keyboard, and move a joystick. They have 10 minutes left on the clock with 2 activities remaining. So this maintenance task worth 20 points, and the final task, the propellant hose connection, worth 10 points. And you'll see the propellant hose connector, the hot pink 3D printed connector, connected to a space hose, connected to a rock on the surface. And this is to try and demonstrate the rover establishing or building infrastructure on the surface. So the robotic arm the rover's carrying has 6 degrees of freedom using cycloidal gearboxes. And everything you see on the rover, as well as all the ground infrastructure and the operators back in the base, it's all designed, built, and integrated by undergraduate students. So every team here is comprised predominantly of undergrad students. And you don't get taught how to build a lunar rover at university entirely, unfortunately. So everything they do is them teaching themselves, seeking out knowledge, testing, learning, and developing. So, and with that, they've scored another few points. right now, you can see through the live stream or up on the Jumbotron the end effector, that gripper joint at the end of the robotic arm, repositioning itself, rotating to try and get a better grip on the joystick so that it can move it to get these points. This is a high fidelity movement requiring multiple degrees of freedom and a solid understanding of how your robotic arm works in three-dimensional space through views of cameras positioned on various places of the rover. So this is a real sort of crucible, the mixing point of all the engineering and design that the students have done, tied in with the operator training. So how well do their operators understand the system and how well can they perform? With some highly dexterous movements, it looks like they've managed to move the joystick up. Sorry, yes, up and then to the left. So this is at face value, relatively simple task, but when you're trying to do it through a computer screen remotely with a little bit of delay, through a robotic arm on a moving platform that doesn't have perfect alignment, it's a true testament to the success and hard work and dedication that the Rover teams put into designing these systems, testing and learning how to use them and operate them in real time. And these are the issues that the real rovers, when they get deployed to the lunar surface, these are the applications and the real-world scenarios that they need to solve. So the Australian Rover Challenge is providing an opportunity for students to actively participate in real-world challenges that they will likely have to do if they end up working on a mission to the lunar surface or any other extraterrestrial surface. With 5 minutes left on the clock, it looks like their last small task for this activity is to rotate that red switch. It looks easy, but I can confirm it is not. So the advantage of different end effectors, or these wrist grippers, is that there's no hard and fast rule of how they should look like or how they should operate. So again, one of the advantages of a Rover Challenge is that there's no right or wrong answer in how teams approach these tasks. So different teams will have different approaches, and that's one of my favorite aspects of student design challenges like this. You get to see how different people approach the same task with different ideas and different sort of innovative solutions. And in practice, let's see if it pays off for them. And with that, a huge round of applause as they manage to flip the switch. And with 3 minutes left on the clock, let's see if they can grab their hose connector and connect it for the remaining 10 points in the task to get all the points available for this activity. So this is the Australian Space Agency post-landing task. And if they manage to get this connector, they will manage to get the remaining points that Project Scorpio couldn't get in time and put them in first place for this current activity. It's truly a race against the clock, as picking up the hose connector, using the robotic arm, driving it over and getting the alignment just right to make the connector. This is truly a demonstration of how good are your operators in operating under pressure in a complex movement. And you'll see the design of the hose connector that Nova Rover is doing is actually to interface rather well with their end effector, their gripper. So their gripper clamps down on that big flat piece at the back of their connector, allowing them to grab it as well as open up the port so that they can easily slide onto the connector, release, and keep that connection tight. So to be awarded points for this activity, you need to not only pick up the connector, drive it over, align it, connect it, but also make sure that connection is solid. Because if your hose connection isn't working and you have a leak, then your infrastructure poses a serious risk to any humans around the area, as high pressure on the lunar surface is not good. It leads to explosions. With about less than 1 minute, let's see if they can make a quick dash. It looks like a scene from The Lion King as it's holding up the hose connector to the audience. And with that, let's have a big round of applause for Monash Nova Rover. With an almost flawless performance, much like Project Scorpio, this last activity is proving harder than expected. Let's see if any of the teams today manage to get this last 10 points. For those tuning in online and for the spectators remaining, with that, it is the end of the Monash Nova Rover run, and I believe we're on a lunch break until, I believe, 2 o'clock. So up next, starting at 1:45, we have the University of Queensland Rover team.
Australia is a nation of creators, aviators, protectors, and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting, and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated, and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials, and digital technologies. Never compromising on safety or quality, always focused on sustainability.
Now they will be attempting to
Solving tomorrow's
interact
problems
with the panel.
today with
So press some
Australia's
switches-
leading
switch some switches, press buttons, type on a keyboard and move the
researchers,
joystick.
scientists, and universities. Developing new military platforms and communications networks, and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line, and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia by Australians for the world.
Okay, are you ready? The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things. The first female Queen's Counsel, Supreme Court Judge, and State Governor, all in one. First in the family with a degree, a black belt, a robot. First Aussie to walk in space. Helped detect gravitational waves. Made lots of babies. World top 100 in all. This stuff. Launched a satellite, revived lost languages, home to 1,600 brainiacs, and a winery, all in the heart of Australia's most livable city. So, what's next? Make history at the University of Adelaide.
Test 1, 2. Yeah, yeah, yeah. Either way. Here or down there? Test 1, 2. Test. Test. Yeah, all good.
Hey man, how you going?
Yeah, good idea.
I got a few questions. Are you like announcing here today?
Yeah, I'm
Obviously,
the MC.
Look, we want.
Check 1, 2. Check 1, 2. Wah.
So to flip between these, see? Great. And then I can just go to that, put it onto that screen for what? Yeah, yeah, great. So,
1, 2, 2.
yeah, nice. All right, stand by. And we're going to go to camera 8. Stand by, mate. Dan. Dan.
So if you're tuning in through the live stream right now or spectating on the sides, welcome back to the 2023 Australian Rover Challenge. We are currently participating in the Australian Space Agency post-landing task. And that involves or challenges the rovers to traverse down the lander ramp, investigate if there's any structural damage to the lander, traverse to each of the pieces of infrastructure on the surface to see if everything's okay. So that's the site evaluation. drive over to the processing plant, download maintenance instructions, perform some maintenance with their robotic arm, and then the last task is connecting that hose, that space hose you can see down on the ground, to the processing plant to establish operations as a surface base on the lunar surface. So up next, or starting as of 2 o'clock, we have UQ Space, the University of Queensland Rover team. They're currently facing some technical issues out back, and we should see them within the next 40 minutes. So the task time, the allocated task time is 40 minutes. And I will keep you updated on the progression of UQ Space.
Australia is a nation of creators, aviators, protectors and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities. Developing new military platforms and communications networks and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia by Australians for the world.
Okay, are you ready? The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things, the first female Queen's Counsel, Supreme Court Judge and State Governor, all in one, first in the family with a degree, a black belt, a robot. First Aussie to walk in space. Helped detect gravitational waves. Made lots of babies. World top 100 in all. This stuff. Launched a satellite. Revived lost languages. Home to 1600 brainiacs. And a winery. All in the heart of Australia's most livable city. So, what's next? Make history at the University of Adelaide.
Hello and welcome back. Welcome back after the lunch break to the third installment of the Australian Rover Challenge right here on the Australian Space Agency post-landing task. The first day of competition. Right now we have UQ Space from the University of Queensland with their rover. They're currently facing some technical issues in terms of getting it moving, but whilst we wait for them to get moving, I'll just explain for those who are tuning into the live stream or watching for the first time as a spectator. This task is comprised of 5 key activities, and the purpose of the task is to try and get students to experience what it's like to deploy a rover on the lunar surface and perform basic site maintenance and evaluation. So all the pieces of infrastructure you see out on the surface will be sent prior to humans or rovers to set up some basic infrastructure that can be used to keep humans alive once they reach the surface. And it is the rover's job to basically unpack that infrastructure and make sure everything is ready to go when humans arrive. So this involves the first thing, which is worth 20 points, the systems check, and this involves descending down the ramp to receive some points, as well as circumnavigating the lander to inspect if there's any damage that has occurred during its descent onto the lunar surface. From there, there will then be tasks to drive to each of the individual infrastructural pieces. So in the center, you've got the communications array, the communications tower. In the back left, up on the hill, you've got the solar panels. And just out of shot, just to the left, you've got the post-processing plant. And all these pieces of infrastructure are serving the purpose of trying to set up a sustainable and operable base on the lunar surface, which is a real-world scenario that's going to be happening within the next decade as NASA, ESA, and the world's space agencies extend their reach to the lunar surface in the hopes of sending humans to Mars as part of the Moon to Mars initiative. And as part of that initiative, the Australian Space Agency, as of, I believe, less than 72 hours ago, signed an amazing deal with, or released the winners of an amazing deal with NASA to send a fully designed and built Australian rover to the lunar surface. And this is called the Trailblazer mission. So 2 winning consortiums of Australian companies have been selected to design a prototype of the rover, with the winning team having their rover sent to the lunar surface to perform foundation service activities, together with a NASA lander to demonstrate that Australians are capable of remote operation of a rover, and to perform some foundation services of picking up a regolith, which is the extraterrestrial soil that covers the lunar surface, and depositing that into the NASA payload, which is the goal is to extract oxygen from the lunar regolith to yield oxygen for humans to breathe, as well as using it in a range of different manufacturing processes, like the manufacturing of steel or wires for use on the lunar surface. One of the other tasks, after they've identified each of the infrastructure to see if it's still functional and read out the status readouts on those supply caches, is to drive over to the processing plant, where you'll see, when we flick to it next, you'll see a white RFID card, which is the same card you use for swiping into your business or to gain access to doors. And the purpose is to try and demonstrate that rovers can communicate wirelessly with the infrastructure on the lunar surface. And to download instructions of what maintenance tasks they need to do on the processing plant, which involves pressing buttons, switching switches, and playing with the joystick. And then after that, it is their job and their last task, worth 10 points, to connect a hose connection, which is part of the space hose on the lunar surface, to the processing plant to establish a supply chain link that the regolith will be deposited in the processing plant, it'll extract oxygen, and then we'll pipe that away to other places, like a landing pad to refuel rockets to build a cislunar economy and industry. So the start time for UQ was 2 o'clock, and they have 40 minutes available to them, so they're 18 minutes in, with 20 minutes remaining for the task. So I've just got confirmation that the base station door is closed and the UQ team are ready to begin their task. So up on the screen right now, let's get a big shout out to UQ Space travelling all the way from Brisbane, Australia. That's right, we are interstate now. You'll see that they're currently on a score of 77.2 from their CDR and SAR submissions. Now, those are the critical design review and the system acceptance review. And these are common flight readiness documents submitted to a review panel to verify how ready is their designs before manufacturing and how ready is their designs before comp. And we use these to down select teams that apply to submit for participation in the Rover Challenge. So both those submissions out of a total of 100 available points. And we're moving. Let's get a huge round of applause again as UQ are moving off the lander platform and begin the descent down the ramp. So with 20 minutes left for the task time, their tasks now are to perform the systems check worth 20 points, which involves circumnavigating the lander and looking for any damage. Then the site evaluation worth 40 points, where the rover needs to travel to each of the supply caches on the surface, so the radio tower, the solar panel, and the post-processing plant. Then the wireless communication task worth 10 points, where they need to download instructions to perform maintenance wirelessly using RFID. The post-processing plant maintenance worth 20 points, where they need to interact with that control panel on the surface, on the side, of the post-processing plant. And then finally, the remaining 10 points, which no team has managed to pass through yet, is the propellant hose connection. And this involves connecting a 3D printed connector that the teams have designed themselves to the propellant hose connection on the post-processing plant. And this is to demonstrate and the final activity that they need to complete to set up this surface base so that it's operable for when humans come. You'll notice the wheels spinning in the regolith, and this is highlighting one of the major issues, or one of, if not the biggest issue for operating a rover on the lunar surface, is that the regolith, the extraterrestrial soil that makes up the fine-grained material that covers the moon, is extremely fine-grained and very, very porous, which means that as you're driving, you have a really significant risk of getting bogged down. Some things you can do to circumvent this is increasing the diameter of your wheels, as well as the grousers, which are the fins that give the wheels traction, to enabling it to almost like paddle or swim through that regolith. And this is a significant issue that has actually posed a huge risk to a lot of rovers, planetary rovers sent by NASA. So for those who will remember the Mars exploration rovers Spirit and Opportunity sent to the surface of Mars earlier in the 2000s, I believe the Spirit rover became bogged down in a patch of really loose, fine-grained, essentially clay, and it got bogged down there and preemptively ended the mission because the rover couldn't move any further, and it stayed there for a couple hundred extra days, or Martian days, called sols, and the rover from its position there managed to complete its task and perform a lot of scientific research in sampling the nearby rocks and regolith and imaging the environment. So it's a testament to how every time a challenge presents itself, how can you take advantage of it and continue to do research and learn about the environment. On the screen right now, you see the live stream live from the base station down on Earth, and this is where the operators receive the video feed and input data from the rover in real time. And this is a real-world scenario that when the students in this Rover Challenge eventually progress into the industry, into the space industry, they'll be working in mission controls like this, a little bit more high-tech than wooden desks, trestle tables. But fundamentally, the roles will be the same. There'll be groups of specialists, some of them working as strategists, some of them working on rover control, some of them working on video feed communications, operating together in a collaborative unit to get the rover doing what they want it to do. So this is a fantastic demonstration of a real-world scenario that students will have to do if they would like to participate in Trailblazer, for example, is how can we work together to operate this highly complex system to perform the task that we want it to do. It's a small anecdote. You'll notice that the base stations are relatively large and luxurious. In contrast, the University Rover Challenge in America, which simulates a mission to Mars, the base stations are quite literally the back of a U-Haul trailer. So you can't really stand up straight, and you can only fit maybe 5 people in there, and it gets extremely hot because you're out in the middle of the Utah desert. So the tents we've set up in the back are quite a significant upgrade compared to the base stations you get when you compete in America. So the UQ team has just called for an intervention which allows the field team and the base team to do some basic maintenance on the rover to try and reset it. So up on the live stream, just previously on the live stream, and for those spectators watching live right now, you notice the fine-grained sand that's building up as loose piles in between the wheels and covering the wheels. This is a real-world scenario that can and will happen on the lunar surface because the material is so fine-grained and loose. It behaves almost like a flowable material at the surface. So trying to think about how to maneuver across this material in a safe and efficient manner is quite a real-world challenge. And the reason why the material is so difficult to work with is because it is the crushed rock, the cooled magma from when the moon formed and geologically evolved as volcanoes erupted, spewed out magma and coated the surface. Over billions of years, that rock gets pulverized by meteorites hitting the surface because the moon doesn't have an atmosphere to burn them up. And over time, it crushes the rock into finer and finer and finer grained particles that we call regolith. These particles are essentially, you can think of them as fragments of highly angular jagged glass or rock fragments. And this poses a huge risk to the operation of any mechanical system with moving parts, because if you get If you were to pour like jagged fine-grained dust into a gasket or a rotating mechanism, it'll jam, it'll wear down, as well as posing a real-world and significant risk to the health and safety of human astronauts, because the dust gets on everything. It is electrostatically charged because there's no atmosphere, which means it not only embeds itself onto the surface of Apollo astronaut uniform outfits, it electrostatically binds itself to the surface. And the material is like asbestos, where if you inhale it, it completely shreds up your lungs. So the Apollo astronauts, if you read through the transcripts or read or watch or listen to some of the video transcripts and audio recordings from the Apollo missions, you can hear them complaining that the dust just gets everywhere. It scratches their visors. They couldn't see it all. It's a real world risk, and how we navigate that risk has yet to be determined. So if any of you have any good ideas, please come tell the Australian Space Agency and NASA. They would love to hear your input. On the live stream, you can just see just how difficult this surface is to drive on. This simulated lunar surface is almost representative, if not easier, than the actual lunar surface. So when you're designing a rover, these are the real-world challenges that you need to navigate. Is how do you maneuver across such a tricky substance where it behaves like smoke when you hit it on the lunar surface, because it just plumes up. And there's actually, it has been observed that the dust that covers the surface can levitate up to 10 meters high, because there's no atmosphere. So it just, the particles repel from each other and can levitate. So the question then is, how do you work in that environment? You've got extreme temperatures all the way up from 400 Kelvin down to 25 Kelvin. You've got the ultra hard vacuum of space. So the vacuum conditions of the lunar surface is so high that we can't, with all our technology, get really close to that high vacuum, that ultra high vacuum, as well as the ultraviolet radiation, the cosmic gamma rays, as well as the lunar dust. So operating on the lunar surface is no simple feat. And we hope that this terrestrial simulation, where we've got wind, sun, some humidity in the air, and some very loose sand, is a good approximation. And it just allows us to really challenge these students for the difficulties of designing a rover for the moon. Some more space facts for you. The lunar regolith is so unique in its mechanical properties because each individual grain is almost like a jagged piece of glass. The way it behaves when it's poured or dug into is almost completely foreign to most materials we have here on Earth. So if you ever inclined to go check out Google, you can type in the Apollo mission trenches that they dug. So they dug about 30 centimeters, I think, or 30 or 20 centimeters into the surface. And the trenches they made had almost vertical walls. So if you've ever been to the beach and you've tried to dig a sand castle or a sand trench, you'll notice that every time you dig down, the walls just collapse in. But on the moon, on the surface, if you dig down, the walls don't collapse. They stay almost vertical. And that's a function of all those particles staying locked together. As well as another really interesting and bizarre phenomenon where the surface is extremely porous. So you can preserve the perfect boot print imprint with sub-millimeter accuracy. You can see the individual treads and perfect square edges of Neil Armstrong's boot on the surface. But if you go down 30, 40 centimeters, it gets so dense that the material behaves like concrete. So the regolith, the lunar soil, compacted more than we can compact material here on Earth. So if you go to a construction site or a road that's being developed, the way they compact it down is like big vibrating, I don't know what they're called, the big vibrating jackhammers, and then the rolling cars with the huge barrels used to compact down the soil. The soil that they compact is actually looser than the soil on the lunar surface. So it's so dense, and the question is, how do you dig into that? How do you build with that material? Is it safe enough to build a base on top of? And these are the questions that, again, need to be answered by students and up-and-coming people working in the space industry. And with that at 2:40 p.m, let's give a huge round of applause to the UQ Rover team. Phenomenal effort, and they've demonstrated just how tricky traversing the lunar surface is. Up next, we've got the University of Melbourne Rover team hailing from Melbourne.
Australia is a nation of creators, aviators, protectors and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities. Developing new military platforms and communications networks and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia by Australians for the world.
For those in the live stream, welcome back to the Australian Space Agency post-landing task as part of the third instalment of the Australian Rover Challenge. Currently competing, starting as of their task time, starting as of 2 minutes ago, is the University of Melbourne Rover team, URT. So they're currently doing some last-minute troubleshooting on the pitch before loading up the rover onto the lander to begin their start time. They will have 40 minutes on the clock to complete 5 activities worth a total of 100 points. The 5 activities include the systems check worth 20 points, where the rover needs to descend down the ramp, circumnavigate the lander, to find out if there's any damage to the lander during its descent down onto the lunar surface. The site evaluation worth 40 points, where the rover needs to traverse to each of the pieces of infrastructure or the supply caches on the surface. So the communications tower, the solar array, and the post-processing plant. Activity number 3 is the wireless communications, worth 10 points, where the rover needs to communicate with the post-processing plant wirelessly using RFID, which is the same technology as your swipe key card. So every time you swipe in, you're receiving and downloading a signal using RFID. The rover is going to be downloading instructions from the processing plant of the maintenance it needs to do, which is activity number 4, processing plant maintenance, worth 20 points, where the rover needs to use its robotic arm to interact with the control panel on the post-processing plant to switch or flip some switches, press some buttons, type on a keyboard, and move a joystick. So this requires some highly dexterous fine motor skills of the robotic arm. And the final task, which no one has been able to achieve today, is the propellant hose connection. So you'll see out on the lunar surface a space hose with a space connector attached to the end of it. And it is the rover's task to connect that connector to the post-processing plant to establish a direct connection from the post-processing plant, which is producing oxygen from the regolith transported to it, to use as rocket fuel or as part of rocket fuel for some other purpose, such as a landing pad refueling depot for rockets coming to the lunar surface and refueling before their journey onwards around the moon. So the hose connector is designed and built by the students. So this is another unique engineering challenge that they need to think about. What's a good mechanism to connect a hose to a piece of infrastructure, as well as, and this is the most difficult part, actually connecting it. So picking up a small connector, lining it up, and getting the correct forces for it to latch on has proven the bane of 2 teams thus far. Let's see if Unimelb can take home the W. Well, let's get a huge round of applause as the University of Melbourne Rover team is traversing down the ramp and is going to get the first 5 points of the 100 available points up for grabs, the descent down the lander. And we're confirming that they have just cleared the lander and they're on their way to the communications tower. So they've just received 5 points. Let's see if they can continue receiving points for Activity 1 and Activity 2, Systems Check and Site Evaluation. That they're off to continue exploring the rest of the site. So we can confirm they've just read out the status readout to the base station judge to confirm that they have a visual feed and a direct control of the rover as they move progressing onto the solar array panel now. So the task start time was 2:45. They're about 8 minutes in with the task conclusion at 3:25. So let's see if they can try and grapple with the 4 tasks ahead of them. So an interesting point that the teams may be struggling with now is that here on Earth we have the sun which sets in a day. So as the day progresses, the angle of the illumination on the status readout changes. And this is a real world scenario that is going to happen on the lunar surface depending on where you are. If you're at the equator or towards the poles, where the sun is on the horizon can change dramatically if you're just moving up or down along the surface of the moon. And the reason for this is because the moon orbits perpendicular on its axis. Now what does that mean? That means that if you were to spin a basketball on your finger, that is rotating about a single axis that is almost straight. So the sun is directly sort of square to that, or perpendicular, which means that the sunlight hits the equator bang on, which means that the surface of the equator can get almost up to 400 degrees Kelvin, which is several hundred degrees centigrade. This is an extremely difficult and hazardous environment to work in, because if you're a human operating in those conditions, you have nowhere to conduct the heat away because there's no atmosphere. So things can overheat dramatically. And on the flip side, when the sun sets, it sets for a month, because a lunar day is a month long, a lunar cycle. So you have a month of daylight and a month of nighttime. So the swing, the diurnal or the lunar day swing, can go from 400 degrees down to about less than 100 degrees Kelvin, and that's absolute. So you can go from several hundred degrees above centigrade down to sub-freezing temperatures. Now, how do you design a robotic system for this environment? It's difficult, it's tricky. You have to design heating elements to keep the electronics alive at night. You have to design cooling systems to keep it cool during the day. And then it gets even more complicated the further you go towards the poles, because as the sunlight hits the equator perpendicularly, as you go towards the poles, sort of up towards the top and bottom of your basketball, any craters or divots topography, because they're spinning on an axis, on a single axis, that means that sunlight can sometimes never enter a region. On the bottom of a crater floor, for example. So we call these regions persistently shadowed regions, PSRs. And that's just a fancy word for saying places on the surface of the moon that never receive sunlight, direct sunlight. So it's so cold there that we've actually recorded the coldest surface temperature in our solar system in the bottom of a PSR on the moon, which was about 25 Kelvin, or 25 degrees above absolute zero. And that's cold. That's very, very cold for the surface. So one of the challenges that a lot of people are trying to figure out right now is, if you're designing a rover to traverse to those PSRs, those cold regions, how do you do that? Because the electronics and the actual chassis of your rover has nowhere to sort of generate heat except from its internal batteries. So there's a real risk of the rover freezing to death, because once you're in those regions, unless you have a nuclear power or reactor like Mars Curiosity and Mars 2020, Perseverance, you have no means to generate power because you have no sunlight and you can't use solar panels. So the current approach that is outlined by several space agencies is for a rover or a a solar panel to exist on the rim of a crater. So like there can be permanently or persistently shadowed regions, you can have nearly year-round regions on the surface of the moon which always receive sunlight, or nearly always. And this is the perfect place to put a solar panel because you've always got energy, and energy is everything on the lunar surface. So you can imagine a rover going back to fuel or recharge at a persistently illuminated region on the crater rim where the solar panels are, and then driving down into the PSR, getting really, really cold, staying there as long as it can, and then quickly scurrying back up to the top of the crater. And then you have lots of ancillary questions, like if you're entering an environment that has been 25 Kelvin for billions of years, and your rover rolls in there at 200 Kelvin because you're trying to stay warm, what happens to the environment that you've just transported to? How do you impact that environment? Are you causing permanent damage to that not the ecosystem, but that environment that you've transported to? So these are ethical questions which raises things like, should PSRs be national parks on the lunar surface? What is the zone of sort of like a museum for the Apollo landers? Are they national heritage? All these questions need to be addressed, and really opens up the forum so that space exploration isn't just for scientists and engineers, it's for ethicists, it's for artists, it's for people studying humanities. It's everyone and everything that we are on Earth in space. And after that spiel, I'd just like to celebrate that the University of Melbourne have completed Activity 1, Activity 2, and are progressing on to the wireless communications task. So now they will try and interact with the RFID card on the control panel of the processing plant. And this is to demonstrate that they can communicate wirelessly and download maintenance instructions. Now, why would you want to do that wirelessly? Because the lunar surface is covered by highly angular dust particles, or jagged little pieces of glass. And if you have a connector like a USB-C cable or Ethernet or something of the like, you're going to get dust all over the surface of that connector, and you won't have a reliable connection. So things need to be wireless, and rovers need to receive instructions from some pieces of infrastructure. So if your antennas are broken for whatever reason, sometimes you may need to use close quarters communications like this. And with that, it is 3 o'clock, so they have 25 minutes left remaining to complete Activity 3, wireless communication, Activity 4, processing plant maintenance, and Activity 5, propellant hose connection. up on the screen right now, you see the Unimelb team base station group. So these are the group of individuals operating the rover, receiving a live feed streamed directly from the rover to their base station antenna. And this is meant to simulate the ground crew on Earth controlling the rover that would occur on the moon. Now, in this Australian Rover Challenge, which is a simulation mission, we've got a real-time link. So the rovers, the operators have a real-time connection to their rovers. But on the moon, it's a little bit far away, which means that there's a communications delay. So the control of a rover, like an RC car, wouldn't really be feasible. So this is one of the reasons why you need to develop a semi-autonomous operation or capability for your rover, so that if you tell it to do something, it is capable of making its own decisions in case you drive towards a large rock or a cliff. So the rover needs to be able to protect itself so that if you tell it to drive to point X, it doesn't bog itself permanently or cause some serious damage. So the base station's up on the live stream. You'll see a large crew with wooden trestle tables in a large, luxurious tent. A little bit of facts for you. If you go to compete in the University Rover Challenge out in the United States Utah desert at the NASA Mars Desert Research Station, which hosts 36 international teams from around the world as part of a simulated Mars mission, the base stations that you get to use are the back of a U-Haul trailer. So you can fit maybe 5 people in there and you can't stand up, and there's no aircon. So I believe the participants of the Australian Rover Challenge are being spoiled right now with some sensational base stations provided and supported by our amazing sponsors who make this challenge possible. And that lovely panning shot on the live stream, the astute of you will recognise the University of Melbourne Rover team has a particular colour scheme for their rover, which is resembling a favourite childhood cartoon with a name beginning with T. Let's see if you can figure that one out. The time is 3:05. There are 20 minutes left remaining for the Australian Space Agency post-landing task for the University of Melbourne Rover team. The remaining activities before them to get the 30 points left are the processing plant maintenance. So it is their job to download instructions using RFID to perform some very dexterous maintenance repairs on the processing plant, which means that it is now the rover's job to press some button, interact with some switches, type on a keyboard potentially, and move a joystick. But it looks like they're skipping that and going straight to the hose connection. And this is activity number 5, worth 10 points. And it is challenging students with designing their own connector so that they can connect a space hose, that propellant hose there, to the processing plant to establish a supply link so that the materials generated by the processing plant, which can include but are not limited to sintered lunar bricks for construction, oxygen or hydrogen as volatiles from the lunar regolith or the soil, which you can use as propellant or you can combine to water for growing food and agricultural purposes, or extraction of metals directly from the soil. No team has been able to achieve Activity 5 yet. It is the most difficult activity for this task and also a new activity for this task. This was not in the previous installments of the Rover Challenge. most of the teams are managing to control their robotic arm using joysticks you would commonly use in flight sims. And this is really tying in that passion for games and just interacting of how do you actually control your rover and really come to terms with that interface between human operator and the robotic rover. So some novel designs of how to control the rover arm from other teams around the world include the development of a small arm on the desk where you move the robotic arm and the robotic arm on the rover moves with it. So it gives you more of a three-dimensional spatial awareness of what your arm is doing. Some other ones include 2 joysticks for controlling the different elbow, shoulder, wrist joints of the arm, as well as then using the Xbox controller. So there are in seemingly endless ways you can try and interact or interface with the rover, and that's one of the beautiful things of the Rover Challenge or student engineering challenges around the world, is that there's no right or wrong answer. The challenge is really up to the students to try and come up with innovative and novel solutions to the tasks. So in the tasks, we challenge them to really think outside the box, and if it works, it works. We're down to 15 minutes left on the clock at 3:10. The task time finishes at 3:25. Let's see if the team can try and interface and pick up with their hose connector. So again, this is a piece that the team have designed and built themselves. So each team have to design a connector that fits onto the space hose, which we've made, and it is their job to connect it to the processing plant. If they manage to complete this activity, it is worth 10 points out of an available 100 points. Up at the live stream now, you'll see a close-up of the University of Melbourne Rover team's Rover, and you'll notice one common theme with a lot of the teams here today, as well as the teams overseas and around the world, is that the wheels that the Rovers use are 3D printed. And one of the novel things about 3D printing is that it enables a lot of really rapid prototyping. So if the teams have an idea, they can often get a prototype out in less than an hour or only a few hours, depending on the size and complexity or the material that they're using. So one of the benefits of 3D printing is that you can use different materials. So you can use flexible materials, sometimes for the treads on the outside, and more rigid materials for the internal spokes of the wheel. So one of the freedom things of 3D printing is that no two wheels are the same. So you'll see that a lot of the teams design, build, and integrate their own wheels, and there's a lot of different things that you need to consider when doing this. Is how big is your wheel? What is the width of the wheelbase? How big are the grousers? What are the geometry of the grousers? Some of you may have looked at the wheels that the Mars Curiosity rover and Mars 2020 rover used. The wheels slightly changed. So they learnt from the mistake or the learnings of Curiosity to optimize the shape, geometry, and size of the wheels for better traction, better control. And it is the same thing that these students are doing each year as they compete and test and continue to learn. It is optimizing and improving on their wheel and drivetrain system, as well as the chassis in terms of suspension. How many wheels do you have? How do they connect to the motors? How do you connect the motors to the chassis? What is your suspension like? Do you have active suspension with linear actuators? So these are all questions that they don't teach you at university, and they need to figure out themselves, and you can only figure that out by designing, testing, building, and competing. So the University of Melbourne team, with just about 10 minutes left on the clock, are abandoning Activity 5, the propellant hose connector, and re-attempting Activity 4, processing plant maintenance. So for teams who cannot read the RFID instructions off the RFID card, you can request the judges to give you the points for a point sacrifice. So it still now allows you to attempt the task, however for less points available had you read the instructions off the card using the Rover. So with just over 10 minutes left, let's see if they can score the last 20 points for this task available to them. So they'll have 4 specific instructions. So one of them may include the movement of the joystick, typing on a keyboard, pressing a button, flipping a switch, or turning a dial. With 4 minutes left on the clock, let's see how many of these small maneuvers the University of Melbourne Rover team can complete for activity 4, the post-processing maintenance. So again, this involves the robotic arm to interact with that control panel on the side of the processing plant to potentially move a joystick, press some buttons, flip some switches, type on a keyboard, and you can see it just bumping straight in. I'd like to reiterate that the Rover Challenge can be highly technical, but at the end of the day, if you achieve the task, if it worked, and I'll just allude to the University of Melbourne last year at this task, managed to complete this activity with no robotic arm, because what they ended up doing was duct taping a shovel to the front and just driving in and pressing a button and getting points. So it just highlights how creativity and novel solutions to difficult challenges is always the solution. It's not always a highly engineered thing, and sometimes things go wrong during development. Sometimes arm failures mean that you can't compete with your arm, and sometimes just duct taping a shovel to the front is the best. Cheer you just heard from the base station operators must indicate that they've just completed the post-processing plant, achieved all the points, and now with about a minute left, I believe are attempting the next activity. And with that, it is the end of the task. Let's get a huge round of applause. University of Melbourne Rover team doing a phenomenal effort. Some fantastic control and some fantastic operation. Up next at the Australian Space Agency post-landing task, starting at 3:30, is the home turf, the defending Rover team of the University of Adelaide Rover team. So the next contenders at the Australian Space Agency post-landing task for the third instalment of the Australian Rover Challenge is the University of Adelaide Rover team. So the beginning of their task time is 3:30. So they've currently on a score. The leaderboard you just saw included the CDR and SAR submission score. Now, those are the critical design review and the system acceptance review that all teams must submit as part of their entry to the Australian Rover Challenge. Now, these are actual flight zones that are very common in NASA systems engineering. There's a systems engineering handbook you can check out on Google if you're ever so inclined. And these documents basically outline the design and intention of the rover team prior to manufacturing and the validation and verification of their rover prior to competing, so that we as judges can evaluate their readiness to the competition. So as we continue to grow as a Rover Challenge, initially we had 3 and then a challenge. Initially we had 3 and then I believe we had 5, and now we have about 8 teams. As we grow each year, soon we will have to down select. It will be a competitive application process. So the University Challenge in America hosts about 36 teams on the field, or not all at once, but sequentially, and there are up to about 100 applicants from around the world. So as we grow as a nation in space and as we grow as a Rover Challenge, soon we may be able to host that many teams, and those documents become more and more critical, because as the students progress into the workplace, these are the documents that they will have to write and submit to a review panel prior to sending anything into space. Because you can't just simply scrap together a few bolts, get some extrusions from Bunnings and just yeet it into the sky. You need to do testing. You need to do development. You need to make sure that it works under extreme temperatures, extreme pressures, vibration, acoustics, radiation. And these are the difficulties that an Australian team will have to do in the not-so-distant future as part of the Australian Trailblazer Lunar Rover mission, which had winners announced about 2 or 3 days ago, comprising 2 Australian consortiums of Australian organisations and companies, which will be developing a prototype rover, an Australian lunar rover, with a winning team or group selected for the final funding round and the development of the final rover. We are slated to launch sometime late 2026 or potentially later, depending how the development of the rocket goes. So the University of Adelaide, the post-landing task has officially started. Now, this does not mean that their task time has started. The base station team need to notify the judges when their task time starts. However, they have an available 40-minute window. So from 3:30 to 4:10 is the available roving time on the field. A little bit more Rover Challenge history for you. The University of Adelaide Rover team have made some significant improvements. I remember last year they submitted an entry that was very overweight. It was very robust, highly engineered, but very heavy. And it raises some important points, as when you're sending things into space, they need to be lightweight, strong, cheap, or relatively cheap, and able to fit in the payload bay of a rocket. Because every kilo that you send to space has a price associated with it. Now that price is coming down dramatically fast with the advent of reusable rockets, but still sending things into space is expensive, so the lighter your rover, the cheaper your mission is, and you can spend more money in the R&D phase of rover development. The other complication is how big is your rover? So the rovers today have a maximum size of about 1.6 meters in every dimension. However, if you check out the lunar rovers that are being designed, developed, and soon deployed to the lunar surface this year, for example, iSpace from Japan and Luxembourg, as well as Lunar Outpost from America, they will be sending rovers to the lunar surface, touching down this year. So they're orbiting right now with the orbital insertion into the lunar orbit. The size of their rovers are quite small. and that means that they're small, lightweight, and perform basic functional tasks. For those new spectators attending at the field right now, and for those tuning into the live stream, the Rover right now is part of the University of Adelaide Rover team, and they're participating in the Australian Space Agency post-landing task. Now, this is the first task out of 4, so there'll be a task every day. So today, Friday, Saturday, and Sunday is part of the 3rd installment of the Australian Rover Challenge. Now, the purpose of the challenge is to try and simulate a mission to the lunar surface. So right now in front of you, you will see a lot of sand, a lot of real fake rocks, infrastructure and hills. And this is simulating some of the terrain that lunar rovers will have to encounter on the lunar surface. And the goal is to try and emulate the Australian Trailblazer mission. So the Trailblazer is the Australian lunar rover set to land on the moon sometime late 2026, maybe later. And the purpose of that is to support, as Australia, NASA's return to the moon with the Artemis program, where humans are returning. So we'll have the first woman to touch down on the lunar surface, and we are going there to stay. So we'll have frequent human spaceflight missions returning to the lunar surface within the next decade. And Australia's role as part of the Moon to Mars initiative, so first we go to the moon to make mistakes and to learn from deploying systems to the lunar surface as we aim to send humans onwards to Mars. And Australia's role in this Moon to Mars initiative is the development of a foundation services rover. So a rover, much like the rovers you've seen today and you will see for the next couple of days, to perform some foundation services. This includes the site inspection. So this task includes 5 activities, including the systems check worth 20 points, the site evaluation worth 40 points, wireless communication worth 10 points, processing plant maintenance worth 20 points, and the propellant hose connection worth 10 points. And the purpose of this task is to get the rover to complete some basic maneuverability activities, so descending down the ramp, driving around the lander, inspecting it for damage, inspecting the other supply caches, so the processing plant, the communications tower, and the solar array panels. This challenge connect to the processing plant. And this is meant to symbolize the processing plant, which extracts resources from the lunar soil, such as rare earth minerals, metals, volatiles like oxygen and hydrogen, which you can use for rocket fuel. And the goal is to set up a supply chain. So the processing plant has a hose connected, and then that can go off to resupply rockets, resupply rovers with fuel. And the difficulty associated with all of that is the students need to do all this within 40 minutes remotely using their rovers. And the robotic arm is an incredible feat of engineering and excellence where you have several degrees of freedom. So every axis or rotation, such as the base shoulder joint, an elbow joint, a wrist joint, adds more and more complexity in terms of control and the actual design of the robotic arm. So it is one thing to design and build a rover, and it's entirely another thing to actually use So, due to some technical difficulties, we're extending the University of Adelaide's roving time by an additional 5 minutes because circumstances out of their control. So their final task time will be 4:15.
Movement. The University of Adelaide rover confidently making its way off of the lander.
For those wondering, my voice didn't drop an octave. That was the lovely John Coulton. So, as an update, the final task time for the University of Adelaide rover team is 4:15. So they've been given an additional 5 minutes for roving time. Let's see if they can descend down the ramp and begin systems check worth 20 points, which is activity 1. And now a reminder, there are 5 activities for this task, and this is the first task out of 4, with each one worth 100 points. And the system check involves the rover descending down the ramp, circumnavigating the lander, checking it for any damage or structural issues that happened as it descended down, using its retro-rocket thrusters onto the lunar surface. And then it is the rover's job to traverse to each of the supply caches on the lunar surface, read out a visual of the status update, so the status of each supply cache to the judges in the base station. Then it is up to the rover to drive to the post-processing plant, which is in the back corner, download wirelessly some maintenance instructions, then perform the processing plant maintenance using the robotic arm up on the top there of the rover. Now, the robotic arm is a complex system which looks like it has about 6 degrees of freedom, which just means that there are 6 different points of movement for the robotic arm to move in. And this is challenging the students of how well does their rover maneuver across the surface? How good is their control of the rover from point to point in avoiding obstacles? How good is their control of the robotic arm in interacting with the environment? How good is their camera feed to be able to read and evaluate the surface readout? How good is their rover operation in terms of managing all that within the given time frame? And last but not least, how good is their operation of the robotic arm in terms of performing maintenance, and the last activity, which is the propellant hose connector, trying to grab the connector that they've made, that they've 3D printed, and connecting that to its receptacle on the processing plant. So no team to date has achieved this last activity worth 10 points, and let's see if the University of Adelaide can take the crown. just an update on time, it is currently 3:54, almost 3:55. The University of Adelaide Rover team has until 4:15 to complete this task. To be awarded the first 5 points, they need to fully descend down the lander. So that means every wheel needs to make complete contact with the ground. None of it can be touching the ramp. So right now we're in an intervention stage where the base station team have nominated to intervene. This means that they can do some basic maintenance and servicing on the rover to try and get it restarted and operational. When a team calls an intervention, they take an immediate 10% penalty of all the available points. So this is the risk analysis and risk mitigation that students need to do and perform is, can we score more points if we reset things and take the 10% loss? Or should we keep trying? And this is one of the many difficult decisions that students and project managers and operators of missions in space need to come to terms with every day, is that there's sometimes no right answer to a decision. You need to make decisions on the fly, and you need to weigh the costs and benefits and risks for it. We got movement. If they get all the wheels off the ramp, they will get the 5 points. Let's keep willing it. This is a huge testament to highlight just how difficult it is to not only design, build, ship rovers over here, but the actual operation of Rover as part of our simulated lunar surface is extremely complex. Many teams have been working for more than a year on these systems, and they are highly complex. They involve people from almost every discipline and every faculty. So the Rover Challenge is a fantastic platform that really brings students together from around Australia and around the world now, as well as from every faculty and every discipline at university. So this is a testament that they're moving and they're still having fun, and that's what the Rover Challenge is all about. It is currently 4:08, and Rover team has been given an additional 5. So they were given an additional 5 minutes. So they will be wrapping up at 4:15, which means the QUT Rover team, so the Rover team travelling all the way from Queensland, will be starting at 4:20. There are 5 minutes left and 5 points up for grabs. All the Rover needs to do is get all 6 wheels off the ramp.
seconds. So as soon as you can hear something new, please let me know. Mine's is buffering.
Really, really moving right now. They've got 1 minute on the clock. Let's see if they can get these last points. So activity 1, there are 20 points on the line right now. If they can manage to read out the status to the base station judges. Amazing pivot steering right there on a dime. The individual wheel control is extremely complex, so hats off to management. Congratulations, University of Adelaide Rover team. I'll just say a huge testament to the team is I think more than half their team got knocked out by COVID, so they're running on a skeleton crew. So another huge round of applause, please, for the University of Adelaide Rover team. Coming up next, in 5 minutes at 4:20, we've got the QUT Rover team, hailing all the way from Queensland. All of our international competitors flow in on very early red-eye flights.
Okay, are you ready? The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things, the first female Queen's Counsel, Supreme Court Judge, and State Governor. World Top 100 in all this stuff. Launched a satellite, revived lost languages, home to 1,600 brainiacs, and a winery, all in the heart of Australia's most livable city. So, what's next? Make history at the University of Adelaide.
So, up now is the Queensland University of Technology, QUT rover called Artemis. Their start time has officially started, but they are able to start at any point. So for any time between now, 4:20 to 5 o'clock, is their window of rover time on the pitch. I'll just point out a nice little shout out to I love the safe carry handles. Looking very nice. And another little piece of information, their rover comes in at a very nice 49.6 kilos out of a total of 50 kilos. So really pushing the limit. And we're back. So can I get a huge round of applause for what QT has managed to achieve with the time that they've had? Not only taking out a rock, but taking home a large amount of points so far. I'll have to repair that later. So the team has 10 minutes left on the field, up until 5 o'clock, so that's the 5-minute buffer that we had from University of Adelaide. And looks like they're coming to the solar array panel up on the pitch. And it is the Rover's job to read the status readout on the solar panel to the base station judge to be awarded the points. And that is part of activity 2, which is the site evaluation. As a quick update, so activity 1 was worth 20 points, which was the systems check, and that was navigating the lander, which you can definitely see they did with the deep grouser marks in the surface. Now they're attempting to complete activity number 2 worth 40 points, which is the site evaluation, which is traveling to each of the supply caches on the surface, reading out the status that is printed on a piece of paper there to the base station judge to be awarded the points. And there's 60 points up for grab out of a total of 100 points, with just about 8 minutes left on the clock, with those last few points comprising tasks which are quite difficult, which is the wireless communication, where the rover needs to download instructions wirelessly using RFID, and then perform those maintenance instructions on the control panel of the post-processing plant. And then finally, and last but not least, connecting the hose connector that the teams have designed and produced themselves to the receptacle on the processing plant, which is the other end of the connector. And that area where the rover is right now, filled with small hills and rocks, is designed to be difficult to traverse, but try and simulate the realistic surface on the moon, which is definitely not flat and definitely has many boulders of varying size. So this is the sort of terrain that rovers will have to navigate on the lunar surface, which comprise large crater walls, like you can see in the top right corner, as well as boulders of varying size from a few centimeters to tens or even hundreds of meters on the surface. And another small point as well, that hill that the rover has to drive up to read the status readout is another obstacle that the rovers have to overcome. Steep inclines with loose soil is not an easy thing to traverse. So this aspect of the task is really testing the teams, or the rovers and the team's maneuverability, how well it can maneuver in all directions, as well as operation, time management, and remote operator control. And for those observing the rover on the live stream or spectating here down on the course, you'll notice that this rover by the Queensland University of Technology, QUT, is quite colourful. And the reason for that is that they have 3D printed many aspects of their rover using different coloured filament. So that filament is plastic, And 3D printing is a technology that allows student teams and people all over the world to extremely rapidly prototype and iterate on their designs. So it enables students to come up with an idea, design it in a 3D modeling software, and then bring it to life by building it layer by layer using molten plastic that cools and hardens to create the wheels and the connection joints you see on the robotic arm before you. And this is extremely useful because it gets students to really get involved with the whole supply chain of design, development, testing, and iteration of their designs. So the full, what would be expected of them when they go into the workforce. And as the rover picks up speed, sending it through the helix, with 5 minutes left on the clock, it looks like they're progressing to activity number 3, which is the wireless communication. This involves the rover connecting wirelessly with the RFID card mounted to the front of the control panel of the processing plant, which you can just see to the left of the screen right now. So that RFID card is what you would usually use to give swipe key access to any of the buildings that here at university or at your workplace. And it is now the rover's job to download a set of instructions from the control panel. And those instructions will tell the base station team what they need to do with the robotic arm, and to interact with that control panel up on the screen now has a bunch of different switches, buttons, a keyboard, and a joystick. And it is up to the base station now to download these instructions and then execute them to be awarded points. One of the difficulties with performing this task, although you can simply just tap your keycard on an RFID scanner with your hand, when you've got a rover on the lunar surface that you're remotely controlling through video screens, trying to get that alignment of the RFID scanner and the sensor is really difficult. The attack angle, or the angle that your rover is approaching the flat RFID card, is really critical because you need a flat, even contact for that data to be read. A good example is if you ever try to pay for something with a credit card and no matter how many times you tap, it just doesn't go. That's an example of how tricky this scenario is. It looks like they might be going back to read the status readout on the communications tower, or potentially going back to the lander. The readout of the status on the infrastructure are worth 10 points. With 1 minute left, there's 10 points up for grab, and this is quite substantial with all the teams being so close in the point scoring system. Every 10 points is really significant here. Can we get a big round of applause, please, for QUT Rover team? Fantastic job and fantastic troubleshooting on the spot just before the task. So thank you very much. And with that, it is the last team of day one of the Australian Rover Challenge, the Australian Space Agency post-landing task. So up on the leaderboard right now is the current standings for the different teams who have completed the CDR and SAR submissions, so the Critical Design Review and System Acceptance Review, as well as the point scoring scheme for the post-landing task. And I believe QUT still need to have their scores updated. So this is task 1 out of 4. So tomorrow we have the excavation and construction task. On Saturday we have the space resources task. And on Sunday we have the mapping and autonomous task. So if you're around any time from today and on the weekend, please come on down to support the fantastic student teams from around Australia and overseas, all the way from Poland, and really get around the Australian Rover Challenge, which is aiming to showcase student capability and excellence in robotics. Thank you very much, and I'll see you all tomorrow morning.
The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things. The first female Queen's Counsel, Supreme Court Judge, and State Governor, all in one. First in the family with a degree, a black belt, a robot. First Aussie to walk in space. Helped detect gravitational waves. Made lots of babies. World top 100 in all this stuff. Launched a satellite, revived lost languages, home to 1,600 brainiacs, and a winery, all in the heart of Australia's most livable city. So, what's next? Make history at the University of Adelaide.
Australia is a nation of creators, aviators, protectors and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities. Developing new military platforms and communications networks and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia by Australians for the world.